July 1966. The M2F2, a wingless test vehicle designed to examine the possibility of returning from space under controlled flight, is tested for the first time. As it glides to Earth, test pilot Milt Thompson finds himself in deep trouble. The Smithsonian Institution's National Air and Space Museum is the most visited museum in the world. Its collection contains some of the most important aircraft and spacecraft in history. Craft that were designed, built, and flown by men and women who have expanded the frontiers of flight. This is the M2F3 lifting body. It's a rebuilt version of the M2F2, which was wrecked in an accident that became famous in the opening of the $6 Million Man television series. The lifting bodies look as if they shouldn't fly at all. They're basically a cone sliced in half lengthwise. This shape, round at the bottom and flat at the top, generates lift in the same way as a wing. The story of the lifting bodies is part of the story of man's attempt to fly to space and back, which continues in the space shuttle of today and the National Aerospace Plane of tomorrow. The X-20 Dinosaur was a U.S. Air Force project that evolved in the mid-1950s. It was to be a shuttle-type vehicle blasted into space on top of a converted ballistic missile. The name Dinosaur comes from dynamic soaring. The X-20 would enter space at about 17,500 miles an hour. This speed would balance the Earth's gravity and allow the X-20 to orbit until it flew back to Earth under full pilot control. The Dinosaur was to be built by Boeing. NASA test pilot Milt Thompson worked on the project.
Neil Armstrong and myself were two of the pilots here at Dryden that were assigned to the program, and we were kind of what you might call consultants to the designer Boeing. We spent many hours up in Seattle. In fact, we rotated on a monthly basis to be there during the development period, and we spent most of our time in the simulator up there developing the flight control and guidance systems.
But the X-20 ran into financial, technical, and political problems and was canceled in December 1963. Milt Thompson was already involved in another program examining the return from space under pilot control, but this time in a vehicle without wings, a lifting body shaped like a space capsule cut in half.
To us, it was more like an airplane, and we felt that ultimately that was the way to come back from space, with a lifting entry configuration where you'd fly back much like an airplane, maneuver and land horizontally.
This very high-performance Pontiac was a key to early tests of the plywood M2F1. It wasn't the kind of vehicle NASA usually bought.
We really didn't tell headquarters that we bought this vehicle. In fact, I think we procured it as a bunch of Pontiac parts assembled rather than as an automobile. Actually, we really didn't tell headquarters about the whole program. We didn't try to conceal it as much as we just didn't tell them what we were doing.
The M2F1 was a very odd-looking vehicle, but it would fly.
This nose glass was the primary window to judge height. In this cockpit, its location, the deck was so broad that you couldn't look down to judge height. We tried to improve the vision by adding some windows on the side. That really didn't help much, so again we resorted to the nose windows. As far as the controls themselves, this outboard surface was the primary roll control, but it also was used for pitch control. The vertical surfaces were the rudders, and this control surface was initially also used for roll, but it wasn't as effective as the outboard surfaces, so we used it only as a pitch control. Now this is our little landing rocket. It had about 250 pounds of thrust for 10 seconds, and if we got into a problem during the landing, we could fire that rocket and it would give us a little more time during the flare and touchdown.
The Pontiac and the lifting body were a strange sight on the lake bed at Edwards.
We ended up being able to tow up to over 100 knots with that vehicle, and we spent months going up and down the lake bed, verifying that indeed it would fly, and mostly building up my confidence to do the first air tow. The only problem we had was dust. You know, we had a 1,000-foot tow line, and the car would be way out ahead of you, kicking up all kinds of dust, and we quite often would get into that dust, and I couldn't see the ground or where the tow vehicle was, so it got a little exciting then. But other than that, it wasn't too bad.
The next step was a big one, a new tow vehicle. This time, the M2F2 would be towed by an airplane, a C-47.
At the low altitudes, you seem to think, well, I can't get hurt here, even though you're going pretty fast, But it was a big step. One of the big concerns, of course, was getting into the prop wash of the tow plane, because this vehicle just didn't have a lot of roll damping. It didn't have wings to give it that roll damping, and so you knew if you got in the wake of the tow plane, you'd go out of control pretty quickly.
This is film of Milt Thompson's first real flight in the M2F1 on August 16, 1963.
The tow up to altitude was, on the first flight, was not real exciting. We got up to the altitude that we wanted to get to and got to the position that we had anticipated for release.
Milt was 12,000 feet above the desert in a vehicle with no wings.
I released, turned back in towards the field, and we had planned a fairly straight-in, benign type of flight, and it worked out quite well.
One of Milt's major problems at first was to avoid the slipstream of the C-47. The prop wash and wingtip vortices of the tow plane could easily flip the lifting body on its back. Milt was making a gliding descent onto the lake bed at Edwards. This test would give some idea just how controllable a lifting body could be.
I maneuvered a little bit to see how well it maneuvered, and then just got set up for the flare maneuver. Got down to the flare initiation altitude and pulled back on the stick to see what kind of response I was going to get. It seemed very solid to me, so I waited a little longer and then began the final flare, and the maneuver worked out very, very well. Very smooth landing, very nice feeling.
Not such a nice feeling, though, for the cameraman near whom Milt decided to practice precision parking. So the first flight was over, and the M2F1 lifting body appeared to handle pretty well. In further tests, other pilots flew it, and it was not always incident-free, as NASA test pilot Jerry Gentry found out.
I just lost control of it, and the vehicle would go into a wild Dutch roll, yawing back and forth from side to side, and then into a roll. And it got to be quite interesting. I found myself upside down over the lake bed about 500 feet above it, and Milt Thompson, my mentor, who was a NASA chief test pilot, was, I'm sure he was going out of his mind and concerned for not only me, but also the vehicle. And I can remember him calling me, "When it gets upright, get out."
Jerry Gentry managed to regain control. His problem was caused by slipstream from the tow plane, and the basic flying qualities of the lifting body were not in question. The lightweight plywood M2F1 had done its job. NASA approved a further extension of the program, and by July 1966, a heavyweight vehicle, the Northrop M2F2, was ready to fly. The all-metal M2F2 was much more advanced than its plywood predecessor. Again, Milt Thompson was the first test pilot.
I was very confident. I had no reservations at all about how well the flight would go, because I had worked with the vehicle for almost a full year before the first flight, developing the flight control system and all the other systems in the airplane. And when you do that, you gain an awful lot of confidence in the fact that the vehicle will fly, and it'll fly right. You just feel it deep down, and you know with all the effort you've put into it, it's going to be a good vehicle.
Milt Thompson knew the heavyweight vehicle would be a different flying challenge.
The rates, both forward and vertically, were much higher. In other words, you were flying at 300 knots versus 100 knots in the lightweight vehicle. Your rate of descent was extremely high, on the order of 20,000 foot a minute maximum. The average duration from launch at 45,000 feet down to landing was less than 4 minutes. And I had figured out that if a guy fell out of the B-52 when I launched, I'd beat him to the ground. So we were what you might call a streamlined brick.
This streamlined brick had no power plant, apart from 2 small hydrogen peroxide thrusters. But there were plans to install an XLR-11 rocket engine, like the one that pushed the X-1 past the speed of sound. In case of battery failure, there was a ram air turbine to power the controls. The controls themselves had 2 independent hydraulic systems. On July 12, 1966, at 45,000 feet, the M2F2 was dropped for its first glide flight.
Surprisingly, again, the vehicle flew quite well. If you didn't look back, you really wouldn't realize that you didn't have wings and a conventional-looking airplane. It felt like a conventional airplane to the control inputs that you made.
At first, the flight went well, but there was a problem lurking in the way the control system had been set up. It led to a pilot-induced oscillation, known to test pilots as a PIO.
I got into a very, very violent PIO. The aircraft was rolling violently, and pitching to some extent. But during that out-of-control maneuver, it slammed my head against the canopy, and that got my attention. So I looked down and checked the control and found that it was in the wrong position, put it back in the position that it should have been in, and the rest of the flight was uneventful. The landing worked out quite well.
Milt Thompson reached a maximum speed of 452 miles an hour in the descent, and his landing speed was around 200 miles an hour. Between July and December, Milt flew a total of 5 glide flights in the M2F2. Then he left the flight side of the program to become NASA's Director of Research Projects at Dryden Flight Research Center. Test pilots Jerry Gentry, Donald Sorley, and Bruce Peterson took over from Milt Thompson to complete the program of glide flights before the rocket engine was installed. Jerry Gentry did not always find it a comfortable experience.
It was a dicey proposition, and I never flew any sort of a vehicle where I felt I was so close, right on the verge of losing control, and yet you had to fly it there to attain the proper speed to make the landing flare. Yeah. So you could just feel the airplane nibbling at you, so to speak. You were essentially just a passenger going up until about the 10-minute point, where you started transferring your electrical power to the M2, or lifting body power, which was done with batteries, turned on your own hydraulic systems, powered up the instrumentation, and got ready for the launch. And the pilots launched themselves in most cases. I got dropped inadvertently once by one of my friends, but the normal procedure was for the lifting body pilot to launch himself. You went into a routine that you had practiced on maneuvers and maintain a certain angle of attack, maintain a certain airspeed, do such and such maneuvers to measure the performance and stability, turn the stability augmentation on and off, and do maneuvers with the airplane to adjudge how it handles. Of course, all this data was being recorded both on board the M2 and was being looked at via telemetry on the ground.
One of the things the test pilots had to work on was getting the landing speed just right.
Normally, you'd be somewhere around 220, 250 knots on downwind. Start a left turn for base down to around 14,000 feet, and you'd be picking up speed, saying generally you're around 240 to 270 knots at the base point, about 14,000 feet above the ground. And then it was the ticklish part where you had to get the angle of attack down to pick up the airspeed. And we felt we needed, and we were pretty correct with it, at least 300 knots to make the flare and get the vehicle on the ground. Of course, unpowered vehicles with a low lift-to-drag ratio like that, the airspeed bleeds off rather rapidly.
While the M2F2 was having its rocket engine fitted, the HL-10 lifting body, designed by NASA engineers and built by Northrop, made its first glide flight. The controls didn't work properly, and the flight almost ended in disaster. Pilot Bruce Peterson managed to land it, and the HL-10 was grounded after the flight for major alterations to the control surfaces. Bruce Peterson now made one last unpowered flight in the M2F2.
We decided to try one more flight with it, and that was Flight 16, Bruce's flight. And the flight went quite routine until it was time for Bruce to turn base leg. There was some confusion. There was a helicopter that was always in the area to provide some an altitude reference He was hovering essentially at 1,000 feet above the ground, which was our pre-flare attitude. But he apparently wasn't in the right position, and Bruce thought it was going to interfere with his landing approach. At the same time, Bruce was pushing over lowering angle of attack to pick up his pre-flare airspeed, and sure enough, the vehicle did go out of control and started rolling violently side to side. Bruce was able to correct it. He was late in getting his flare completed and getting the landing gear out. As a matter of fact, the landing gear were coming out just as he touched down. And of course, the vehicle then rolled over several times. It's quite fortunate that he wasn't hurt worse than he was. The vehicle, fortunately, was built like a locomotive, and the pilot was almost totally encased in steel structure.
This is the cockpit film of Bruce Peterson's approach. You can see how the vehicle rolls wildly before he regains control.
We had instrumentation on him during that accident, and the highest G-force that he saw was 4.5 G, which is very survivable. The good thing about it was that no one was killed in that accident, and in fact, he would have survived without any injury at all, except on the last flop over. It broke the canopy and slammed his face into the lake bed.
Bruce Peterson survived the crash with severe injuries. After almost 2 years of hospitalization and treatment, he returned to work as a test pilot. Milt Thompson was concerned that the accident would halt the program.
We were afraid that some of the people in headquarters might want to cancel the program as a result of that. In fact, I had to go back to headquarters and try to explain the reason for the accident, and then subsequently convince them to rebuild the vehicle.
Eventually, he gained approval for the M2F2 to be rebuilt with a third fin for greater control. It took a long time for the decision to be made and for the necessary research to be completed. At the same time, the HL-10 was also out of action, while design changes to improve its controllability were studied. The program came to a halt for over a year while the research necessary to correct the problem was completed. By early 1968, the HL-10 was ready to fly again. On March 15th, Jerry Gentry climbed into the cockpit for the first of a series of glide flights to check out the design changes made since the vehicle was grounded over a year before. It was only the HL-10's second flight. Jerry Gentry had to hope the NASA engineers had done their job in solving the major control problems that had occurred on the first flight.
I flew it after it had been modified, and it was by comparison to what Bruce had experienced, it was a real dream to fly. And the engineers had done a marvelous job in cleaning up the handling qualities and improving the performance of it.
By this time, NASA was interested in the development of a winged shuttle-style vehicle as a follow-on to the Apollo program, which was about to place Neil Armstrong on the moon. The X-15 program was winding down, and the lifting bodies received a new lease on life because of the need to gather data on unpowered landing approaches after re-entry to the Earth's atmosphere. By October 1968, the HL-10 had been fitted with its rocket engine, and Jerry Gentry climbed into the cockpit for its first powered flight. Unfortunately, he was not to be the one to experience a lifting body under power for the first time. A few seconds after ignition, the XLR-11 rocket engine failed. 2 weeks later, John Mankey was dropped from the B-52 at 35,000 feet and ignited 2 chambers of the XLR-11. Under half power, the HL-10 climbed more than 7,000 feet and reached a maximum speed of 523 miles an hour. The question had finally been answered. Under power, the HL-10 lifting body would fly pretty much like a normal airplane. Since 1967, the Air Force had been testing a lifting body of its own, the X-24A, designed and built by Martin Marietta. It was different from the NASA lifting bodies in both shape and control system, but it used the same XLR-11 rocket engine. By early 1970, it was flying satisfactorily under power. Just after it made its first flight, a familiar shape re-emerged from a long rebuilding program. This is how the M2F3, rebuilt after Bruce Peterson's major crash, looked when it arrived back at Edwards, ready to fly again. The major modification was the addition of a third fin in the center of the rear fuselage. It was designed to increase the stability of what had been a vehicle with marginal handling qualities. Veteran X-15 test pilot Bill Dana was given the job of testing the M2F3. He made the first glide flight in June 1970, and then in October dropped from the B-52 for its first flight under rocket power. This flight was cut short when the rocket engine failed, but in 1971 it made several supersonic flights, testing a new fly-by-wire control system, a forerunner of the kind of system that would be used on the Space Shuttle. But the lifting body that was most closely related to the Space Shuttle in appearance and aerodynamics was the Air Force's X-24B. Through 1974 and 75, it flew several missions to gather data used in the Shuttle project, and also increased the speed and altitude envelope of the lifting body program. It flew faster and higher than any of the other lifting bodies, reaching 74,000 feet and Mach 1.76. When it retired in late 1975, the lifting body program ended.
Overall, we had some problems with each of the different configurations, but they were not very serious problems. Most of them were handling quality kind of problems where you had to tweak the flight control system, so to speak. And it ended up where all of the vehicles were very flyable. Again, they flew like typical fighter airplanes.
We felt that the tests that we ran proved beyond a shadow of a doubt that those kind of vehicles could be controlled and landed quite safely.
In my opinion, the lifting body program gave the space side of NASA the confidence to select a lifting entry configuration for the next generation spacecraft, and that, of course, is the Shuttle, rather than, say, a capsule type vehicle. There was serious consideration to using the capsule configuration for the Shuttle mission, but luckily they went to the lifting entry concept. And although the Shuttle is not a lifting body, a lot of the technology that went into the lifting bodies was transferred into the Shuttle.
The Space Shuttle's final design was strongly influenced by the fact that the lifting bodies and the X-15 had made safe, unpowered approaches and landings from high altitudes.
Having done that and having demonstrated that it was an extremely achievable thing to do operationally. I think really gave a lot of confidence in bypassing putting some kind of an air-breathing engine on the shuttle to assist in the landing, in the final landing approach. Saved the program a tremendous amount of money, tremendous amount of headache.
The shuttle concept survived the cutbacks to the space program in the early 1970s. North American Rockwell was selected as prime contractor in 1972, and what emerged after a lengthy evolution was one of the most complex machines ever devised.
I certainly recognized and appreciated it was an extremely complex airplane. I also understood the reason why it had to be so complex. The total redundancy that had to be available in the machine. To place a vehicle and a crew in a space orbital environment, you just cannot afford to have the kinds of failure scenarios and come back home real quick that you have the luxury of, even in an airplane.
The first shuttle, the Enterprise, was destined never to go into space. It would explore the atmospheric flight characteristics of the orbiter after mid-air launch from the top of a modified Boeing 747. For a prospective shuttle pilot, preparation was a huge challenge.
The Space Shuttle was a great deal more complex machine than the X-15 was. It had more systems on it, and they were redundant, which added to the complexity of the entire system and the entire pilot task. So there was a great deal of academic classroom work, studying and learning systems. There was a great deal of simulator work. And prior to the Enterprise flights, of course, we really had no demonstration that the airplane was going to fly like the simulator indicated it would. But I must say that the engineers who had built the simulator models did an extremely good job. It was a terribly close representation, very high fidelity representation of how the Space Shuttle, how the Enterprise was going to fly, and the subsequent vehicles that went into orbit were going to fly.
2 crews were chosen to pilot the Enterprise. Their training program in the simulator and in the classroom was long and intensive. Fred Hayes from the Apollo program was the commander of the first crew. Joe Engel from X-15 and Apollo was commander of the second. Joe Engel's pilot was Dick Truly, a NASA astronaut and Navy commander. Fred Hayes' pilot was also from the Apollo program and from the Air Force, Charles Gordon Fullerton. The group flew a number of different airplanes. A Boeing 707 gave them the feel of handling something around the Enterprise's weight. They also flew a converted A-7 Corsair, the Digitac airplane. It was fitted with a digital fly-by-wire system in which a computer interprets the pilot's control movements, modifies them to suit the airplane's performance, and passes them on to the control surfaces. But they also had an airplane specially designed as a flying shuttle simulator.
We had a very, very good airborne trainer. In addition to the T-38, which we could configure into performance-wise pretty close to the shuttle and fly the approaches and get the visual picture coming into the runway, the 38 didn't give us the handling qualities that we were to encounter and to have to endure with the shuttle. But the shuttle training airplane, the Gulfstream, was very, very accurate in representing the handling qualities and characteristics.
The left side of the Gulfstream's cockpit was set up just like the shuttle. The right side had a conventional control system. The airplane also had an onboard computer and a third seat for another trainee. On September 17, 1976, the Enterprise was rolled out of Rockwell International's assembly building at Palmdale, California. The band played the theme from the television series Star Trek, 2 crew members of the fictitious Enterprise were there, and the children of Palmdale were well aware of the connection between the new space shuttle and the Enterprise they saw on television. On January 31st, 1977, the Enterprise made the 36-mile journey from Palmdale to NASA's Dryden Flight Research Center at Edwards. A large proportion of the Antelope Valley population turned out to see it as it inched its way along. The Enterprise was to be the first of 5 shuttle orbiters built under the original contract with North American Rockwell. The program would be a major factor in the economy of the Palmdale-Lancaster area, so many of the families watching the Enterprise's progress had a real stake in its success. At the Dryden Flight Research Center, the Enterprise was fitted into the rig that would place it on top of a converted Boeing 747 for a series of atmospheric test flights. The rig was known as the MDD, or mate-demate device. On February 8, 1977, the Enterprise was mated to the carrier aircraft. Pilot Fitz Fulton had to fly what he called the biggest biplane in the world.
I had known Fitz Fulton, who was commanding the 747. I had known Fitz for a long, long time at flight test at Edwards there. And there's just no one that I respect anymore as a big airplane driver that really knows his business than Fitz. So I didn't have any concerns in that respect. Quite frankly, didn't have any concerns at all in the captive flights. It was a matter of checking out certain systems that we wanted to verify and confirm their performance before committing to free flight. And as I say, Dick and I were so busy that I think both of us, the time during that flight went by in a real big hurry.
By the time Joe Engle had his first flight, there had been 5 tests with no one aboard the Enterprise. Then came a series of 3 flights in which the Enterprise, with crew aboard, remained attached to the 747. They had a special purpose.
Primarily to get some aerodynamic data on the relative lift of the orbiter at different conditions while it was mated to the 747, so that we would know that a good clean separation was available.
On August 12, 1977, Fred Hayes and Charles Fullerton made the first separation from the 747 carrier aircraft. The first free flights were made with a streamlined tail cone covering the shuttle's engine nozzles.
We had a very aggressive series of flight test data points that we wanted to achieve in that configuration, even with the tail cone on. And again, once we had separated from the 747, it was an extremely busy profile all the way down to touchdown. As most test flights are, it was, to me, again, it was a terribly rewarding experience to sit down and plan and work out what kind of maneuvers were necessary to fly in order to optimize the data for the engineers to get their parameters that they were desiring, and then to fly those maneuvers as precisely and accurately as possible, and still recover the airplane.
In Joe Engle's first free flight, the Enterprise made a 1.8 G left-hand turn, and the control surfaces and split rudder air brakes were tested. Then came the long, steep approach to the lake bed at Edwards, with the Enterprise coming in to touch down at over 200 miles an hour. All 4 shuttle crew members found the Enterprise with the tail cone on a very straightforward vehicle to fly. In this format, the landing approach was relatively shallow. When the tail cone was removed, there would be much more drag generated around the rear of the vehicle, and they knew that it would be a different proposition. Joe Engle was a veteran of many test flights and lakebed landings in the X-15. He could directly compare the behavior of this new vehicle with one of its ancestors.
It was a much more highly augmented flight control system than the X-15 had. And I think in that sense, you could recognize its personality was that of an electric airplane. There was no doubt in your mind that the inputs that you were making to the hand controller or to the control stick were being looked at and interpreted by computers, and then in their attempt to answer you with an airplane response was very apparent. But the vehicle was an honest flying vehicle. The shuttle is a very solid, honest flying vehicle.
With the tail cone off, the crews had much less flight time, and the descent was much steeper than in the earlier tests. The Enterprise was coming down at a rate of more than 10,000 feet a minute, in a descent that was very similar to its other ancestors, the lifting bodies. Even so, the Enterprise proved that as well as landing on the wide expanse of Edwards Lake bed, it could also touch down safely on a conventional runway. After 2 test flights with the tail cone off, the Enterprise's job in the desert was finished. It had proved the space shuttle could fly. By early 1978, it had become too expensive to upgrade Enterprise for launching into space. NASA was short of funds, and Enterprise was below the engineering standard needed for spaceflight. So Enterprise's next stop would be the Marshall Space Flight Center at Huntsville, Alabama, for a series of ground vibration tests in which the Enterprise and the shuttle's external fuel tank would be subjected to vibration forces like those expected during a shuttle launch. To prepare for Enterprise, a full-size mock-up was suspended in the Marshall Center's test facility. On the way to Huntsville, the Shuttle 747 combination dropped in at Houston, where a huge crowd gathered for its first look at the new face of America's space program. For Enterprise, the welcome was ironic. Her future was not in space. She was taken to Washington, D.C. for eventual display at the National Air and Space Museum. On April 12, 1981, John Young and Robert Crippen boarded the Shuttle Columbia for launch into space. Their task on this first mission was to check out the shuttle's orbital systems and payload doors. As Columbia blasted out of the atmosphere, Joe Engle and Dick Truly were preparing for the second Columbia mission. They would have some frustrating delays.
We had several delays on the pad, and they were frustrating, but I think, and they were frustrating for us. I think both Dick and I remember, Dick Truly and I both expressed to each other kind of independently, our concern was more in our friends and that we had invited down to watch the launch. The guests, many of them couldn't stay over. We knew we were going to get to go no matter how long we had to wait.
On November 12, 1981, their 4-day wait was over.
I was amazed at the level of vibration that was there when the solid rocket boosters were ignited. The main engines burn relatively smooth, and they're about 470,000 pounds thrust each. But the solid rocket boosters, when they ignite, they're about 2.5 million pounds thrust each, and they're, to me, a much rougher burn than I had anticipated. It didn't seem very spacey to me when we were lifting off at first 2 minutes while they were burning. There was a lot of vibration, a lot of noise from mechanical rattling back and forth inside the cockpit of things that were stowed down in middeck. The acceleration right at liftoff was not extremely high. It was 1.5 Gs because of the total weight of the vehicle. Then it built up to 3 Gs, and the engines would throttle to maintain 3 Gs maximum. 3 Gs is certainly not incapacitating by any means, but over a period of 8 minutes, which the insertion time takes, about 8 minutes and 45 seconds, reaching switches becomes hard. Your arm gets tired reaching for things. I was not able to turn my head in the pressure suit. I had to reach up with my hands and turn the helmet so that I could look out to the side or look around the cockpit. So it was more of a awkward thing than a discomforting thing.
About 2 minutes into the flight, at a height of 21 miles, the solid rocket boosters separated. 7 minutes later, the external fuel tank was dropped off and Columbia entered orbit. It was Dick Truly's 44th birthday. He and Joe Engle had arrived in space by shuttle for the first time. They were welcomed by a new set of sensations, including prolonged exposure to zero gravity.
Zero gravity is an extremely pleasant environment to live in and an easy environment to work in. But the fluid shift and the sensors in the inner ear and things all tend to realize a strange environment. And if you're not careful, which we were not initially, on what we ate before we went into orbit, and to realize that less fluid in your body is a desirable thing to have when you're going into a zero gravity environment, we were, many of us felt less than 100%. I don't think anyone was really incapacitated as far as not being able to do anything. But it was frustrating to be in that situation of an opportunity to fly and to perform the experiments and the tests and not feel 100%.
There was a disappointment for the two astronauts. The mission was planned to last 5 days, but a problem with one of the fuel cells reduced it to 2. Nevertheless, the main experimental objectives, among them testing the remote manipulator arm, were achieved.
Test pilots are trained to kind of divorce themselves from the emotional things, but I think the thing that I remembered the most was a very unpiloty thing that had to be done, and that was just to float over to the window and look back at the Earth. And that was the most awesome experience that I have ever had in my life. And I think everyone comes back and feels pretty much the same way. To look back at your Earth and to see the whole thing at once is just a tremendous experience. Yes, it is expensive to go into space with the shuttle, and I think that we should be able to accept that up front. It's a pioneering vehicle. I don't think there's any doubt that knowing what we know now and using our hindsight, as we always are able to do, we can now design and build a vehicle that's more economical to take things into space. Whether it's practical to expend the R&D funds for it at this particular time is something that naturally a decision has to be made on. But I think for what we have learned and what we have gained from the space shuttle in learning and knowing how to go into space and how to take people and satellites and payloads of all kinds, and being able to go up and take people up and do repair and recovery missions and retrieval missions with a vehicle like the shuttle, it gives our nation a very unique capability that I don't think is available in any other mode or any other nation right now.
That capability owes much to the X-15, the lifting bodies, and the Enterprise, and the data they gathered above the lake bed at Edwards.